It is Chapter 3, Interpolation and Polynomial Approximation. For given discrete data points, interpolation is to construct a continuous function passing all the data points. If a polynomial is constructed and if data points are representing a function, then the constructed polynomial is an approximation of the function. In this chapter, we'll study how to construct such interpolating polynomial, and we'll try to analyze the accuracy of those polynomials. Okay, let's go to section 3.1, polynomial interpolation. Here we have a theorem, Weierstrass approximation theorem. F is a continuous function defined on the interval AB. Then, for each choice of epsilon positive, there exists a polynomial p of x such that distance between f of x and p of x is bounded by epsilon for all x in the interval. This means that for continuous functions, we can find polynomial which is arbitrarily close to the continuous function. Theoretically, it's true. However, in reality, sometimes it is not easy to find such polynomial, particularly when data points are decided. Then sometimes it's impossible to find polynomial uniformly near to the given function. We'll see later on some examples and limitations given from reality. Okay, let's see this example. Here, f of x is e to the x, a simple function. Then we can find Taylor polynomials, P0, zeroth order, and P2, second order, fourth order, sixth order. If we plot them, then we can see here, and this red one is original function e to the x, and now there is P0, zeroth order, so there is constant, and second order, fourth order, sixth order. As order increases, you can see better approximations. Okay, that's for simple function is working in this way, so that for e to the x, if you are choosing very high order, and then this inequality for arbitrary epsilon, you can find a very high order Taylor polynomial, so that this inequality will be satisfied. This is a simple example. Okay, here we have a polynomial interpolation theorem. Xn, x0 to xn are n plus 1 distinct real numbers. Then for arbitrary values y0 to yn, there is a unique polynomial Pn of degree at the most n, such that Pn at xi is yi. If you start with n plus 1 distinct points, then for arbitrary height for each point, this y0 to yn will be height, the function value at here the points, and for arbitrary heights, and we can find the unique polynomial Pn such that the polynomial will pass every points. The uniqueness is quite simple. Once we start with Pn minus Qn, then again, Pn minus Qn is nth order polynomial, and at n plus 1 points, the value is 0, which means that, and this polynomial must be completely 0, so that here Pn and Qn must be identical. For existence, okay, in mathematical theory, uniqueness and existence, then uniqueness proof is relatively easy. But for existence, sometimes very complicated. When you construct the function required in the theory, then you can prove existence. Here, we'll try to construct nth order polynomial and satisfying that equation. So we proceed inductively through construction. For n equals 0, and here we can easily construct a function in this way. P0x is y0, so that now the first point is only we consider a constant polynomial in the beginning, and here P0x equal y0. Now we assume that we obtained a polynomial p sub k minus 1 of degree k minus 1 with here from x0 to xk minus 1, the pk minus 1 xi is yi. So we assume this one, and we try to here find the pk passing one more point. In order to do that, from pk minus 1, and we are adding this term. Then for this pk, using the assumption here, now we can figure out here now. Okay, and first of all, the pk, because this is now kth order term, and pk is now the polynomial of degree k. And also, once you put here xi for pk, and I is from 1 to k minus 1, then here this portion will be yk, and then now this portion must be 0, because here the product is from x minus x0, x minus x1, and up to x minus xk minus 1, so that once x is chosen from here x0 to xk minus 1, then this term will be 0. So that pk at xi, I is moving from 0 to k minus 1, then now it's the same as pk minus 1 xi, which is yi, right? So pk will pass the points xi, yi for I equal 0 to k minus 1. Now we'll decide the ck such that here pk at xk is yk. Now here if x is xk, then pk minus 1 xk, and we have this term which must be yk. Now we start with distinguished points, so that this product cannot be 0, so that here after moving this one to the other side, and we try to divide the terms by that one, so we can reach at the ck. With this computation, now we found pk, which will pass the extra point xk, yk, because we chose ck such that pk at xk is yk. So for all the points from x0 to xk, the pk will pass all the points, so that is the case level polynomial. So this is mathematical induction. In the beginning, P0 is constructed, and then assuming pk minus 1 is constructed, then pk can be made. So that once pk made, then pk plus 1 will be made again, up to k is n. So this is argument of mathematical induction, recursive construction. Okay, that is from Newton. So that Newton tried to construct polynomial by adding one more point and with one more degree higher polynomial, and in this way Newton tried to construct nth order polynomials. Okay, so here that form of polynomial is called the Newton form. Newton form of the interpolating polynomial is given in this way, and we can write this one into this compacted form. And here, okay, for ck, now we have that product. This is product part, and I is from 0 to k, and ci, the coefficients, and here x minus xj product. Okay, and here if we write down the first three cases detail, then P0x is C0. Of course, C0 must be Y0. And P1 is now C0 and C1x minus x0. And P2 is now that P1 plus C2, x minus x0, and x minus x1. You can continue here. So these polynomials are called the interpolating polynomials in Newton form, or Newton form of interpolating polynomials. Okay. Now we'll illustrate the Newton's interpolating polynomial in this example. We'll start with here function f of x is sine x, x minus 1 plus 1, and we chose 1, 2, 3, 4, 5 points. You don't have to get order the points. These are distinct points. And here we'll try to find the Newton's interpolating polynomials which pass all the points. Okay. Now in maple implementation, and here we just for comparison purpose or function evaluation purpose, we defined in the beginning the function, and xk is 0. That is the first point now, 0, and xy is x and okay, that's xk and f at xk, so that 0, f of 0. This is the first data points. For that one, we try to make polynomial interpolation, and here using Newton's method. And once you see the constructed polynomial, then that is constant, because now we are using only the single point. And then for 0.5, that is this point x1, and we add to p0, we add this point, and so that p1 is made. If you see p1 of x, then you can see this one. That is now c0, and there's a c1. Okay, this portion is here c1, and that one is now x minus x0. x0 is 0, so we have c here. Okay. Now x2, that is x2. Okay. Now, so that x2 is now added. Then you can see here now that is c0, c1, x minus x0, and c2, x minus x0, and x minus x1. Now we are adding c4, x4, and x4, y4 is added to get here now a third of the polynomial. That is now extra term, right? Okay. In fact, this is x3. Now finally, we're adding x4. So x4, y4 is added to a third of the polynomial to get fourth of the one. So that is last added term. That is c4, x minus x0, x minus x1, x minus x2, x minus x3. Okay? In this way, you can construct and here one more higher order, and by adding one more points. And let's see the picture. Okay, that is now x0. This is x0, and passing this one is exactly this one, and x1 is this point, so that you can see linear one, and x2 is this one, so that passing here this 30 point will be quadratic, that one, and x3 is at 2, so that point, so that is passing now here and like that, and that one. Okay, this is p3, and final point is at 1.5, so that here possibly around there is a final point. By adding this one, now is really almost identical to the function. It's a really good approximation. Okay, now once Newton form of a polynomial pk is given, then here we'll consider how to evaluate the function value, polynomial value. For example, in this way, it is given, then x value is now given, then we have to evaluate this thing. Okay. Now here we'll consider how to evaluate, and by using nested multiplication, or sometimes it's called the Horner's method. We can evaluate the function value quite easily. Okay, this is now the compact form of the Newton form of interpolating polynomial. Of course, over there, dj is the same as x minus xj. Once x is given, then now it can be written in this form. Now, that is here the formula, and we write down this one opposite way. Then, except this one, everywhere over there, it each term include now d0, so that we can factor out d0, and that is here in the middle part. And then except this one, again, every year it is d1. So again, we can factor out d1, and we continue this factoring. Then we can recheck here. Okay, now so that here ck dk minus 1 plus ck minus 1. After getting this one, dk minus 2 is multiplied and ck minus 2 added. And this quantity is multiplied, and now ck minus 2 is 3 is added, and so on. So that here in this nested multiplication, through this nested multiplication, you can get the function value much more efficiently than if you try to compute this one here as given in this form. By using this nested multiplication is really much more efficient. Practically, for nth order polynomial, you need for each k over there, one multiplication, one addition, so that eventually number of operation required is 2k operation. So that much better. Okay. Now this nested multiplication can be implemented in this way. So here, one addition, one multiplication, one addition for given D and C array, and you can get it. Okay. Now here, we can use this part and try to compute the ck for the Newton polynomial. So that here, this is an algorithm. So after evaluating, here now we can find the C values. So looks like if you follow the algorithm, then you can figure out that this clip will produce the ck, the coefficients of Newton interpolating polynomial. And this is a choice. However, a more efficient procedure exists to get the coefficients of Newton polynomial. Later on, in section 30.2, we'll learn so-called divided differences, and along with that technique, we'll compute the coefficients ck much more efficiently. Okay, let's see this example. Now, we start with a polynomial, third order polynomial, and we chose here the data points, and 5, -7, -6, 0 for x values. The corresponding f values are given here. From this data, once we try to get third order polynomial, Newton interpolating polynomial, then that must be identical to the given function, because the 4 points decide the polynomial uniquely. These 4 points are chosen from a third order polynomial, so that even though the Newton form of interpolating polynomial looks different from the given function, that must be identical. Okay, here for comparison purpose and graphical purpose, we define f, and these are data points here, and we make Newton form of interpolating polynomial. The output is given in this way. Now, this portion must be C0 plus C1 and x minus x0. So that now that portion must be C0 plus C1 and x minus x0. The x0 is 5, must be given in this form, but output of maple is given in this one. Here in practice, here C0 is 0, C1 is 2, so that this quantity must be this one. It is happening because now we are using student version of numerical analysis. I guess this maple, these guys, the company should not do this way. Student version will be cheaper than the original version. However, this output is changed in this way, then it's not a good way of making software. Anyway, now here there is 1 plus 2 times x minus 5, and that is the C2 of that, and C4 is 4, and that one. So that is Newton form of interpolating polynomial. Now, if we expand, then here that polynomial is the same as the original one. Okay? So that here, if we try to get remainder and error, then error is 0. And here, if we draw the Newton form of interpolating polynomial, then here that okay, that is now this green is Newton form of interpolating polynomial, and here that blue curve is the original function. They must be identical, and this red square are the data points. Okay. Okay, and also we try to print out divided difference table. Then later you will learn what it is. Now, once we use divided difference, then the diagonal will be the coefficients for this Newton form of polynomial. C0 is 1, C1 is 2, C2 is 3, C3 is 4. So by manipulating this table, if you're taking the diagonal values, then these are just the coefficients of Newton interpolating polynomial. Okay. Now, let's try to find the Newton form of the interpolating polynomial of this given data. Okay, here there's x0, x1, x2. So we start with P0. P0 of x is C0, which is now their value 1, right? Now, P1 of x is same as P0x plus C1 x minus x0 x minus 2. And for that one, we have to decide the C1 so that at here minus 1, so that we have to decide the C1 such that P1 at x1 equal y1. That is now 1 plus C1, and x1 is now minus 1 minus 2, which must be y1 4. So after moving this one 3, there's a minus 3, so that C1 equal minus 1. So we conclude here P1 of x equal 1 minus x minus 2, right? Now, finally, we have we should construct P2. Okay, P2 of x as P1 of x, 1 minus x minus 2, and plus C2 x minus x0, x minus 2, and x minus x1, x plus 1. Now we have to decide C2 such that P2 at x2 must be y2. So here P2, now x2 is 1. Okay, that one is 1 minus 1 minus 2 and plus C2, and x is 1, 1 minus 2, and here 1 plus 1, which must be minus 2. Right? Okay, now from this one, here, that is 1. Okay, this is 1, now minus 1, so the plus 1, and plus here C2 times, that is minus 1 plus 2, so the minus 2 equal now minus 2. So that 2 has moved to minus 4, and so the C2 must be 2. Okay, so this value is replaced by 2, then that is the interpolating polynomial in passing all the points, okay, in Newton form. Okay, that's the end of part 1, and we'll continue in the second part. Thank you.